Okay, let's dive in. How do humans actually acquire language? I mean, seriously, think about it for a second. We've got this incredibly intricate system, right? Language full of hidden rules, subtle variations, all this stuff even native speakers can't really explain consciously. And yet somehow tiny humans, kids, they just seem to soak it up. They go from, babbling to making complex sentences unbelievably quickly, and everyone does it pretty much the same way. How does that even happen? So today, yeah, we're doing a deep dive into some really foundational ideas trying to tackle that question. We've got some fascinating source material here, and basically our mission is to use it to understand the language learner. What state do they start in? How might they learn? What's this incredibly complex knowledge they end up with as adults? And what role does experience play in all this? And you'll definitely want to stick around because the sources throw in this really surprising comparison. Something about bees. Bees navigating using the sun. How on earth is that relevant to a kid learning grammar? Well, we're going to try and connect those dots.
Yeah, and the sources really lay out this core problem for us, don't they?
Hmm.
It's about trying to figure out how do you characterize a learner, someone who can arrive at this very specific, very complex language system and do it so fast, so reliably. Especially when the language they actually hear, the input, well, it can be pretty messy and incomplete in real life.
Right. That's the puzzle. Because the end point, the adult state, what someone who speaks a language natively really knows, it's way more than just vocabulary, isn't it? It's this deep, often totally unconscious knowledge of structure.
Absolutely. The
Yeah.
sources really emphasize the kind of implicit knowledge we all have as native speakers.
Right.
It's not just knowing, John read the book, sounds okay, and the book read sounds wrong. It goes much, much deeper. It's knowing these incredibly subtle constraints.
Like, which words can go where in a sentence, or how certain words hook up with others.
Exactly. Think about questions, like with who. You can ask, who do you think Mary likes? Fine. But you also just know, somehow, that there are limits, especially with things like contractions like wanna. You can say, who do you want to talk to? No problem. But you can't say, who do you want to talk to you? Just sounds wrong, all right? Even though on the surface it looks kind of similar.
Right. And nobody sat you down and taught you that rule specifically. You just internalized it. These incredibly intricate rules.
And the complexity isn't just, within English. It's also how languages differ. We know English usually goes subject, verb, object. John ate pizza, pretty standard. But then you have Japanese putting the verb right at the end, like John got pizza to beta. A really obvious difference.
Okay, clear enough.
But the variations go way beyond word order. They get really subtle, way below the surface. The sources compare how languages handle pronouns, for instance. In English, if you say, Billy thinks he is smart, well, he can refer back to Billy.
Sure. Or it could be some other guy.
Exactly. It doesn't have to be Billy. He could be someone else entirely.
Okay.
But then you look at other languages, like Russian, the equivalent sentence structure. Billy Egoya, well, there the pronoun he, me might actually have to refer to someone other than Billy.
Really? It can't be Billy.
In some interpretations or contexts, yeah, it just cannot confer with Billy in that structure. It's this incredibly abstract, non-obvious rule about how pronouns link up. And it varies subtly from one language to the next.
Wow. Okay, so the result of learning, the output, is this deeply complex, highly specific system of rules. And it varies in these really sophisticated ways across languages.
And for researchers trying to study this, well, it's challenging. Because this complex knowledge inside a child's head isn't always easy to see or, measure directly. Plus, like you said, the input a child gets is often messy. False starts, sentences that trail off, background noise.
Exactly. So you've got a super complex target system, potentially noisy, messy data to learn from, and a learner, the child, who can't exactly explain what they know, and yet,
learning happens incredibly fast.
Yeah.
And remarkably uniformly across children.
The speed is just striking, isn't it?
It really is. The sources point out that by 18 months, long before they're speaking in, like full adult sentences, children's very first little multi-word utterances already show basic syntactic patterns of their language. Things like where the verb typically goes compared to other words, they're already picking that up.
Wow, already?
Yeah. And the uniformity might be even more amazing. These key developmental milestones, like babbling around 6 to 8 months, saying first words around 10, 12 months, they happen on a very similar schedule for kids everywhere. It doesn't matter what language they're learning. And even children with severely limited input, like kids who are congenitally blind, or deaf children who aren't exposed to sign language early on, they still hit these linguistic-like milestones in a similar developmental window. It really suggests it's something very robust, something internally driven about the whole process.
Okay, so given this complex target grammar, the messy input, and this incredible speed and uniformity, how do children actually get there?
Well, this leads us straight into a major hypothesis that runs through the sources. The idea that the initial state of the learner, the baby's mind, is not a blank slate. The idea is that the child's mind comes already equipped with some kind of fundamental structure, maybe a blueprint, that's specifically designed for learning language.
Like a built-in language toolkit? Is that the idea?
Precisely. That's a great way to put it. The sources often talk about this concept as a language acquisition device, or LAD, basically some kind of specialized mental machinery. And this LAD is thought to provide the learner with some foundational knowledge, a set of principles that are common to all human languages.
And this is what's often called universal grammar, or UG.
Yes, exactly. UG is the core concept here. It's proposed as this innate foundation that lets the child actually make sense of the language they hear around them. So instead of having to sort through every logically possible way that words could combine or sentences could be structured, which would be infinite, really UG drastically narrows down the possibilities right from the start. It helps them sort of zoom in on the relevant linguistic data and form only a limited set of guesses or hypotheses about the specific grammar of their language.
So it's like having, I don't know, a preset filter. Or maybe a template that guides the search, makes it more efficient.
That's a very good analogy. The sources give the example of a really basic operation in language, sometimes called merge. It's essentially the fundamental tool that lets us take linguistic bits, words, phrases, and combine them to build bigger structures, like sentences. Now, the human mind could potentially do all sorts of weird combinations, right? But UG might constrain the language learner to only consider operations like merge for building sentences. That kind of built-in constraint just dramatically shrinks the huge space of possible grammars a child might otherwise have to consider.
Okay, this is getting a bit abstract, maybe. Where do the bees fit in? How does bee navigation help us get a handle on this idea of an innate template?
Ah, yes. The bees. It's a really fascinating analogy used in the sources, precisely to make this idea more concrete. So forager bees, they need to navigate using the sun's position. Of course, the sun moves across the sky during the day, and its path isn't just a straight line, it's nonlinear. And that specific path changes depending on where the bee is on Earth and the time of year. So bees somehow need to know the sun's position relative to direction. They need a sense of the local ephemeris function, which is basically just the specific path the sun takes in their location at that time.
Right, and that's definitely not something you sit down and teach a bee, is it?
Exactly. So this study, Dyer and Dickinson back in '96, which the sources mentioned, they investigated this. They raised bees in a controlled lab environment, and they only let these bees see a part of the sun's daily journey, maybe just the last few hours before sunset, for example. So this is kind of like a child getting maybe limited or incomplete linguistic input. You see the parallel.
Oh, okay, yeah, I see. Limited data.
Then they tested the bees on overcast days when they couldn't see the sun directly. They watched the bees' dances. That's how they communicate direction relative to where the sun should be. The big question was, okay, they only saw the afternoon sun. How would they estimate the sun's position at other times, like in the morning?
What did they find? Did the bees just kind of guess based on the little bit they saw? Maybe draw a straight line backwards?
That's what you might logically expect, right? Simple extrapolation. But nope, that's not what happened. The bees didn't just linearly extend the path they'd observed. When they were estimating the sun's position in the morning, remember, having only seen the afternoon sun, they estimated it to be roughly 180 degrees opposite from where they'd last seen it in the afternoon. And they showed this big shift around noon in their calculations, not just a simple, slow movement.
Whoa, that's wild. So they didn't just follow a simple rule based only on what they saw.
Right. Their behavior strongly suggested they weren't just using like a memorized list of sun positions or calculating a simple linear rate of change. They behaved as if they were using an internal representation of the sun's actual nonlinear path across the sky.
So they had some kind of pre-existing internal map or template maybe of the shape of the sun's movement, even though they hadn't actually seen the whole thing.
That's exactly the powerful interpretation offered in the source material. The bees seem to possess an innate template, a built-in approximate idea of the ephemeris function. Perhaps something like a general template for a path that involves a significant shift around noon. Learning, then, for the bee becomes the process of refining that innate template, or maybe filling in the details based on the specific experience of the sun in their local environment.
Okay, get the analogy now.
Yep.
So Complex learning, even from limited experience, can happen quickly and reliably if the learner starts with some kind of pre-existing template or structure that guides the learning. And the hypothesis for human language, then, is that universal grammar is that innate template. It guides kids to learn the complex grammar of their specific language from whatever input they happen to hear.
That's the parallel exactly. And so the whole research enterprise in language acquisition isn't just about describing the complex grammar adults end up with. It's also crucially about trying to characterize this proposed innate structure, universal grammar, and figure out precisely how it interacts with the linguistic data a child encounters to produce the knowledge of their specific native language.
Okay. But since we can't exactly give babies, a written test on pronoun binding rules, researchers have had to get really creative, haven't they, to figure out what children actually know about language at different stages? The sources give us a peek into these methods.
Yes, absolutely. Studying language acquisition in children is definitely tricky. I mean, their general cognitive abilities are still developing,
Mm.
and their ability to actually show you what they know is limited by things like, well, how well they can talk or pay attention, or even just point or manipulate objects.
Right, you can't just hand them a grammar workbook and say, fill this out.
Exactly. So researchers use a whole range of different approaches. There are what you might call naturalistic methods, things like keeping incredibly detailed diaries of a child's language development, or analyzing huge computerized collections of recorded child speech, like the child database.
That sounds like you'd capture real spontaneous language use.
You do, and that's a huge plus. When a child actually produces a particular sentence structure spontaneously, that's pretty strong evidence they have some knowledge of it. You see how often they use it, in what contexts. But the downsides are significant too. You don't really see what they think is ungrammatical. You might not be sure exactly what meaning they intended, and you might just get unlucky and never hear them produce a specific, maybe rare type of sentence you're actually interested in studying. They just might not say it while you're recording.
Which is where controlled experiments come in, I guess.
Precisely. These experimental tasks are specifically designed to test particular hypotheses. They try to elicit certain behaviors or measure reactions in a controlled way. For really young infants, passive looking and listening tasks are invaluable.
Like you show them different pictures while they hear different kinds of sentences.
Yes, exactly. You basically capitalize on what babies do. Naturally, they look at interesting things, they listen to sounds. So researchers might track, say, how long an infant looks at a picture that matches a sentence they're hearing compared to one that doesn't match. Or maybe how long they listen to grammatically correct sentences versus sentences with errors. Their looking patterns or how long they choose to listen can actually reveal if they understand something about the sentence structure or its meaning even before they can talk.
Clever. And what about as kids get a bit older?
Then you can use tasks like nonce word tasks. The classic one everyone knows is the WUG test. You show a child a drawing of some made-up creature, you say, this is a WUG. Then you show them two of these creatures and say, now there are two. And the child typically will say, WUGs. Since WUG is a totally made-up word they've never heard before, producing WUGs shows they haven't just memorized the plural form. It shows they know the rule for forming plurals in English, adding an S sound, and can apply it to a new word. It tests their generalized grammatical knowledge.
That's a great way to see if they've learned the rule itself, not just, memorized a list of words.
Exactly. Researchers also use things called act-out tasks. Here, you might give children little dolls or toys and give them instructions using complex sentences, like, make the dolly touch the horsey after the horsey jumps over the fence. You see if they can act out the sequence correctly based on understanding the sentence structure and words like after.
Testing comprehension through action.
Okay. And there's also elicited production.
Elicited production.
Yeah, that's where you try to set up a situation, maybe using pictures or puppets, that's specifically designed to make the child want to produce a particular kind of sentence you're interested in. For instance, maybe you show them a picture of a cat chasing a mouse, and you try and get them to use a passive sentence. Uh-oh, what's happening to the mouse? Hoping they'll say something like, the mouse is being chased. You carefully craft the prompts and the whole scenario to try and nudge them towards using the target structure.
I see. Trying to gently pull the language out of them.
Kind of, yeah. And finally, for slightly older children who can understand the task, you can use judgment tasks. A very common one is the truth-value judgment task. Here you might tell a little story, maybe act it out with puppets. Then, one puppet says something about what happened in the story. The child's job is just to say if the puppet was right or wrong, basically, judging if the puppet's sentence is true or false according to the story they just saw. This is actually really powerful for testing how children interpret sentences that might be ambiguous or sentences with complex structures that affect the meaning. For example, you could test how they understand a sentence like, every horse didn't jump over the fence, which actually has two possible meanings for adults. You see which meaning the child gets.
Wow. Researchers really are incredibly innovative, aren't they? Finding all these ways to try and peek inside the child's linguistic mind.
It's absolutely essential because, as the sources really underline, making real progress on understanding language acquisition depends crucially on finding these clever ways to gather reliable data from the actual learners, the children themselves. That's how we try to figure out what their initial state, that UG, might look like, what learning processes they're using, and how they eventually arrive at that incredibly complex adult knowledge we all have.
Okay, let's circle back then and recap this journey we've taken through the material. We started out by just highlighting the mind-boggling complexity of language, right? That final adult state, all those deep, often unconscious rules about sentence structure and meaning that native speakers just know. Then we look at the acquisition process itself, how stunningly fast it is, how uniform across kids and cultures, and how robust it seems to be. Happening on a similar timeline even for children, with very different kinds of experiences, different sensory abilities, and despite, the challenges of potentially messy input and output data.
hmm And we explore the really powerful hypothesis that emerges from these observations, which is definitely prominent in the sources we looked at. That this incredibly efficient and robust learning is possible because the learner, the child, doesn't start from zero. They don't start with a blank slate. Instead, they come equipped with some kind of innate structure, universal grammar, that acts as a sort of blueprint or a template. And this UG significantly guides the learning process, helping them make efficient sense of the language they hear.
And that unexpected connection to the bees navigating with what seems like an innate template for the sun's movement, that really helps drive home the core idea, doesn't it? A biological system coming sort of pre-equipped with a structure that then gets fine-tuned by experience in the environment.
Yeah, I think the bee example is a great way to visualize how a pre-existing template can constrain and really guide learning, whether it's a bee learning the specific path of the sun where it lives, or a child learning the specific grammar of their native language from the words and sentences they hear around them. It's the same principle of innate structure plus experience.
And importantly, none of this is just, theoretical hand-waving. We saw the really ingenious ways researchers actually go about gathering data from children. From carefully watching where infants look, to asking toddlers to act out complicated sentences, or having older kids judge whether a puppet is talking sense or nonsense.
Yeah, these methods are absolutely crucial. They're how we actually piece together this remarkable puzzle of how humans acquire language. It's real science, grounded in careful observation and clever experimentation.
So let's bring it back to you, the listener. Just think about the children in your own life, maybe your kids, nieces, nephews, or just kids you see around. Think about how quickly they seem to just absorb language, the incredibly subtle ways they master grammar and meaning, often without anyone ever explicitly teaching them the rules. It really is one of the most amazing and maybe underappreciated human abilities when you stop to think about it.
And this core idea, building on the source material we've explored today, the idea that language acquisition seems to be guided by some kind of initial innate structure. Well, it prompts a really fascinating question to ponder, doesn't it? If our minds come prepared with some kind of blueprint specifically for language, what might that suggest about the nature of human knowledge more generally? And maybe reflect on your own fluency in your native language. How much of what you intuitively know about its grammar, its structure, what sounds right and wrong, how much of that is something you think you learned only from the language you heard, versus how much might be something that your mind was, in a sense, already prepared to figure out based on some kind of universal human design for language.
Definitely something to chew on as you go about your day, navigating your own linguistic world.